Thank you for choosing this session, and thank you for Simon to introduce me. So, as you see, 7 people are working together on this project at our side, and referring back to the invited talk yesterday, 3 of them are women, actually. It's a pity that they could not come today, so it's my task now to present the results. So what is our motivation? Probably everybody agrees with me that we are expecting megacore computers in the near future, or not very near future, but in the near future. Megacore computers which are highly heterogeneous, that may contain CPUs, GPUs, specialized computing elements, or general purpose computing elements, and we would like to write software for these machines. And this software should be optimized both for performance and for energy consumption. It's not very easy to write such programs if you don't have the right constructs to structure our programs. So if you want to think in parallel, if you want to really write large-scale parallel applications, we need the appropriate tools for that. For instance, we need high-level programming constructs. We don't need to worry about deadlocks and other communication problems. It should be somehow part of the system, part of the design to eliminate such discrepancies. Is it turned off? Oh, okay. The communication facilities should be somehow taken away from the hand of the programmer and should be left to be implemented by the system, by the runtime system. And finally, we have to be able to engineer the performance characteristics of our applications. So the performance should be considered part of the design from early on. And it's not only applies on new software, but we have to restructure existing software, legacy software as well. So we need some tools to help us in these tasks. So my talk will introduce you a tool which is able to find parallelizable code in some code base, is able to help the programmer to make the right decisions on how to turn his mostly sequential code into mostly parallel. And for that, it allows the programmer to reshape the program so that the parallelization can be introduced to the software. I think this kind of software, this kind of tool should be very useful for many of us. All the work has been carried out in the ParaPhrase project, Parallel Patterns for Adaptive Heterogeneous Multicore Systems, which is a FP7 project running from 2011, and it's going to terminate this year. So if you are really interested in this topic, then you could check the results of this project. But well, even now you can visit our website or tweet us. Today and yesterday, you have probably heard talks from our project. Wojciech from AGH was giving a talk yesterday, and Chris Brown from St. Andrews, I think he had this talk in this room just before lunch. So what are the main ideas of the ParaPhrase project? The project aims at improved programmability of heterogeneous parallel architectures by allowing us to express parallelism in a structured way. So we can use high-level parallel patterns to express how the parallelization of the application should be carried out. Patterns like map or reuse or task farms or pipelines, divide and conquer. These are quite general patterns. There are more domain-specific patterns as well, like orbit or stencil. And once we express the parallel structure of our applications using these high-level patterns, then we can use the runtime system to map the components of this system onto the existing hardware, taking care of the optimal use of resources. and even remap the components of the application if the hardware resources are changing. The ParaPhrase project addresses two language environments, C++ and Erlang, but guess what? I'm going to talk about Erlang this time. So the patterns that are familiar for many of us are like the form, the pipeline, map, reuse, divide, and conquer. I will mostly talk about the form today, and a little bit about the pipeline. These are the two patterns that we currently can address with our tool. So what is the approach of the ParaPhrase project? Well, in ParaPhrase, we say that if you want to parallelize an application, we first have to identify the components that can be run in parallel. And these components should be fairly independent from each other. They should not interfere with each other if we run them in parallel. So they should have some hygienic behavior. And when we identify those components, then we can introduce the patterns for describing the parallel behavior of the application. So we structure the components in the parallel program by turning the patterns, the recognized patterns, into some basic implementation. We have a skeleton library that allows us to construct patterns. And of course, in this process, we will take performance and energy consumption into account as well. Once we have introduced some parallelization and we have done with some profiling, then we might have find out that we still need to restructure application. So we need tools to do the work, the transformation, the program transformation work during the introduction of the skeletons into the code, and also during the restructuring if it is necessary. So we propose to use a refactoring tool for this purpose. I mentioned that Chris had a talk just before lunch. He's not here, probably he's drinking his well-deserved beer somewhere. Let me just tell you in a few words what he was talking about. So he said that there is a scale library for Erlang and also for C++, but the scale library for Erlang allows us to describe parallel patterns with some domain-specific language. I will show you a few examples on that can be applied on some inputs and produce some outputs. And these kind of patterns can be mapped onto available hardware resources, both CPUs and GPUs. All this can be carried out using a refactoring tool, Wrangler. Simon gave a talk yesterday about how to use Wrangler for refactoring Erlang programs. And I will show you a few examples during this talk as well. So for instance, if you want to have a pipeline in your application, then you should specify something like this. So you say that I have the inputs, and I would like to apply a pipe on these stages. Of course, this should be done only when I have lots of inputs. So the list of the inputs is flowing in the system, and the list of outputs is flowing out of the system. Similarly, I can very easily express a form. I have some input. I have some inputs, and I apply the same worker activity a couple of times. And again, I split the long list of my inputs and allow the workers to produce the outputs. So in this case, I need a process that splits the input into among the workers, and another process that collects the outputs and returns the value, the least value produced by this construct. But all these details are hidden by the library, so I don't have to worry about these low-level process creation and communication issues. And the whole thing is completely compositional, so you can define more complex patterns using these simpler ones. For instance, you can describe an end-calling optimization algorithm using a feedback skeleton, a form skeleton, and a pipe skeleton. So what I do here, I describe this computation with this complex structure. So it's a feedback that takes a pipe. The first stage of the pipe is a form. Inside the form, I'm doing this find solution function on the inputs. And in the second stage of the pipe, I do the pick best function. This seek here is a special skeleton expressing components. So this function is turned into a component using this seek skeleton. Now let's see a simpler example. For instance, a matrix multiplication. You have a dot product taking a row and a column, and then in the multiplication function, you take a matrix in as a list of rows, and another matrix as a list of columns, and you compute the dot product of all the rows and all the columns. So it would be nice to identify how this can be parallelized automatically. So our goal is to develop a tool that is able to do this pattern identification. So the tool should be able to find that, yes, this is a place in the code where you can introduce a skeleton to describe the structure of the parallelization. And if you have many such places in your program, then the tool is able to choose the best ones to introduce parallelism. Of course, in a large-scale program, you will have millions of pattern candidates, but only a few of them is worth to actually turn into a parallel pattern. So our tool will be able to rank and suggest the best candidates. And as well, we can do some shaping of the code so that the introduction of these skeletons becomes easier. For instance, if we take this multiplication function, we can introduce a form which allows us to compute each row of the resulting matrix in a separate worker. So this is the code is actually quite similar. It didn't change a lot. So the main computation is done here. So this is how I compute a row in the output. And this is turned now into a function that takes a row from the left matrix and produces an output row. And I will pass this function to each of the workers in the form. In this example, I have 16 workers. Of course, you have to tune this value based on the available hardware resources. So when you design your application, you express the structure of the parallelization you want to use, but you also need to set the constants properly. You have to somehow work with the available resources and split the resources among the different components. So I would like to show you how this works in practice. So let's party. It's gone. mouse is doing really strange things with me. Oh. Do you know how to make this bigger? Can you see it? No? I can't see it.
The font, you want the font bigger in the buffer? If you do, oh no, that's the font. You get the fonts down there, system fonts, set default fonts. No.
No. Oh my god. Ah. That's bad.
Set default font, do it.
How to do that?
You go to the actual options. You do set default font. Up.
Here. Oops. Yep.
And then go up to, that's it. 17.
Oh, that's fine. Oh, that's better. Ah, cool.
And if you close the bottom buffer,
Okay, sorry for that. I'm a VI person, so Emacs is, kind of dark magic for me. So our tool is called PartParty Parallel refactoring tool for Erlang. And I can turn this on. And as you see, new menu item appears here, the party menu item. Oh, this is not, the font of this is not changed, unfortunately, but I will tell you what you can see there, if I can see. So, for instance, I can do some pattern discovery. It takes a few minutes, so I have a save me kind of menu item, which allows me to view the previously executed, the previously obtained results. So if you don't mind, I will use this menu item rather than running the search just at the moment. If you're interested in how this works, just come to me and I'll show you. So in this case, a browser will pop up. Again, I need to change it. And this browser will show me the possibilities that my tool has found in the code. For instance, it proposes me to introduce a form in this file, in the matrix. That's one variant of the matrix multiplication. If I introduce a form with 20 workers, then my tool thinks that I will achieve a speed up, a very good speed up. So this is a recommended transformation by the tool. Of course, I will have pattern candidates which are not really good ones, not very good candidates. They are not recommended, like this one. If I do introduce form transformation here, then with 6 workers, I can achieve 2.4 speed up, which is not very good. So suppose I want to see this one. This is a bit more complex. This is a farm of farms, so I will have to introduce 2 farms in this example. And on 24 cores, this might give me almost 19 speed up. So if I click on this one, I can see that there is a list comprehension which I can turn into a form, and there is a call to the lists map function which I can also turn into a form. It should be highlighted where this thing is.
if you put a space into the EDIF window,
Here?
type space.
Yep. Great. Good to have a Wrangler expert around. So this was the original code. And the shaping would turn this code into list comprehension. Yeah, it's equivalent actually, but is more appropriate for introduction of the form. Okay, so I like this. So you type bang, Q. Oh yeah, Q. Yes. I mean, yes. Okay, so my code has been changed a little bit. Now, this is a list comprehension where I can introduce a form. Oops, oh, I have to select it. Tick, tick, tick. I introduce a form, say 22 workers. Oh, 12 workers. Yes. I'm not going to preview it this time, just say commit. So now you have the form introduced. And then again, you can do something with this inner list comprehension. In this case, you cannot introduce scale form directly because the head of this list comprehension is not exactly in the shape that is required by the transformation. Here, I need a function call with a single argument. So this is not really the case here. I have a function here with 2 arguments. So I have to shape this a little bit. Again, party, refactor. I have to fix the head of this list comprehension. Commit. Of course, the code is not as nice as it was before, but still semantically equivalent to the original one. But now I can introduce a form here. So I say form introduction, 2 workers, yes, commit, yes, and now I have the other form as well. So this is how you work with party. How much time do I have?
12 minutes.
It's fine. So what are our expectations against our tools? Well, this will, of course, change the way we think about parallelism. Or at least, our tool is able to completely redesign our software automatically. Or at least, show all possible places where we can introduce parallelism into our code. We can predict speed up exactly. And the tool does everything by itself. We don't need any interaction with the tool. It's safe, completely safe, and completely automatic. Of course, these are completely false expectations. None of them is true. You should not expect such behavior from a tool. What can we do? We can find many places where we can introduce parallelism. We can predict speed up more or less precisely, not very precisely. The level of precision depends on the depth of the analysis we perform and the precision of the cost model that we use. The more precise cost model we use, the more precise predictions for the speedups are. But if you use a very complicated cost model, then the tool becomes very slow, and of course you don't want to use it anymore. So there should be a trade-off between applicability and precision. The tool is very good if you are a smart programmer and know how to use it. But it won't work by itself. Sometimes it needs input from the programmer. Sometimes needs interaction with the programmer. But all in all, it can allow you parallelize your program in a very simple way, so you don't have to think too much. You don't have to read code too much. You you get some easy parallelization, not much effort, much gain. So that's what we try to offer to you. So the key idea behind our tool is that we can predict speed up by measuring the sequential execution time of certain components in the program. We just generate some random input data, measure the execution time, and try to estimate the parallel execution time with a cost model. And if this estimation is good enough, then we can predict the speed up quite precisely. So this is the big picture of the tool. We have lots of Erlang code here. At the moment, we are working on integrating OpenCL code into the tool. Chris talked about OpenCL plus Erlang code refactored together, introduce skeletons that are really heterogeneous. We don't do that at the moment. We just have Erlang code at the moment. So we do some static analysis on this Erlang code, and we try to cost the possible pattern candidates. The static analysis will find us some pattern candidates that we can benchmark, and by applying a cost model, we can come up with some speed-up predictions. So we rank the best candidates and present them to the user. And the user can apply refactorings to introduce the required skeletons into the code. So this first phase, this pattern candidate discovery, is no magic, actually. It just goes through the whole program and tries to identify certain syntactic structures and also investigates the semantic properties of the code at those places. For instance, it will fire on these comprehensions, or it will analyze recursive function definitions. Of course, you can only apply a transformation if the preconditions of that transformations are met. So we have to analyze the side conditions of the transformations as well. And what makes the tool really useful in practice, we need to apply some heuristics to improve the suggestions. So for instance, our tool can identify multiple ways to introduce skeletons in this code. It will measure some certain components in this code fragment, and it will, of course, identify the best possible candidate for parallelization. So how does the analysis proceed? We have different kinds of analysis combined together. Since in Erlang we can call functions dynamically, we need a good dynamic call analysis, which is supported by module scope analysis and static call analysis and some data flow analysis. And we also need some type analysis. I will tell you later why, but you can find it out. We need to identify operations that work on lists, for instance. So we need to find out the list values in our code. So we need to infer types for certain expressions. And we also need to do some side effect analysis, because the side conditions of the refactorings are often based on the side effects, the possible side effects of certain expressions. So how can you do this kind of analysis? We have a tool for that. That's a long story. This tool has been created like 7 years ago. It's good for refactoring, it's good for static code analysis and transformations. Has lots of nice features. It constructs a program graph. It's not just an AST, not just a abstract syntax tree, but it constructs a more informative program graph, semantic program graph from the source code, stores it persistently in a database, and we can use this semantic program graph to collect information about the code. We can find dependency among program entities. We can identify bugs and track them down and investigate them. We can also share information among team members And we can also refactor the code using this tool. I'm not going to details about this tool, just skipping these slides because I need to hurry a bit. So the pattern candidate discovery uses the infrastructure provided by Refactoral. At the moment, we can identify list operations like list comprehensions. That's target number one. A certain library calls like I show you list map is a good target. And you also try to identify map-like recursive functions. So we analyze recursive function definitions and try to decide whether they operate in a similar way to the list map function. At the moment, we are able to propose candidates for task forms and pipelines. I'll skip it. A map-like function is something, it's a function, it's a recursive function. Okay, recursive function, now I need some call graph to decide whether a function is recursive, so I need a kind of analysis to decide whether a function is recursive. It takes a parameter p, which must be a list. Okay, I need some type analysis to decide whether a parameter is of type list. And then I need a control flow graph to investigate the different execution paths in this function definition. And all the recursive execution paths must satisfy certain conditions, like they should return a list R, where the head of this return list should not depend on the complete list coming into the function, only the head of that list. And yeah, this is a dependency analysis again. And the tail of the resulting list should be the result of the recursive call on the tail of the input. And other parameters of the recursive call should not be changed when we call recursively the function again. And for the non-recursive execution paths, we require PB, the empty list, and the function should return the empty list. So this is a characterization of map-like functions. So if we can, using our analysis, we can identify these map-like functions, we can turn them again into a map and then into a task form. One important concept here is the concept of components. A component is something that is done by a stage of a pipeline or done by a worker of a task form. They should be quite independent from each other. So there should be some side effect analysis that tells us that, okay, these components are possible to run in parallel. There are many sources of side effects in Erlang, as we know. Message passing, global variables in C code, but even exceptions can cause impurity. Kostis made some experiments on how much percent of typical Erlang code is pure. It was below 10%. So it's not much. So we don't want to just deal with pure definitions. We will work with hygienic components rather. So hygienic components can be characterized by the resources they use and how they use those resources. So if you have resources in our source code like ETS tables, then we can decide whether a component, whether the component alters this resource, just reads this resource, or does not read or write this resource at all. And we can identify component sets which behave well together. There is a simple rule. If a component C1 alters a resource R, then another component in the same component set should not use read or write this resource. And if a component set is constructed of components with this property, then we can run them in parallel, so we can use them in the body of a skeleton. So these are the analysis that we do. So once we have this analysis, we can do the benchmarking and then apply a cost model. For benchmarking, we split up the candidates into small fragments, and measure the execution time of those small fragments on randomly generated input. So we need to compute the free variables, which will be the inputs to these expressions. We assemble a new module of these small expressions. We can instrument it with time measuring functions. All this can be done very easily using the infrastructure provided by Refactoral, so it's really fun to use Refactoral for these purposes. And this is done actually at runtime, so we generate these things while our tool is running, while Party is running. And then we load this module, generate some random input and profile the data, and make some statistics, and this is how we benchmark the software. So this random input might be really scary for the first moment. It's not always meaningful, of course, but if you want to do some automatic timing, profiling, then there's no other way but generate some random input. So we try to find out the type of our free variables and use quick check to generate random data based on the types. But for that, of course, we need some type inference, which is good enough, which is not the success typing provided by Typer, for instance, because Typer is happy to provide any as a type for everything. So we need more conservative typing. At the moment, we are using Typer with specs. It works for many cases, but we have to work on another approach, a better type inference algorithm for this purpose. So once we are through this, we can apply the cost model. We have a formula that we can use to compute the estimation for the parallel execution time based on the sequential execution time. But as you see, there are some constants in this formula that need to be calibrated to the hardware that we are going to use to run our application. So that's why we had the calibration phase on the diagram. But once we are through this application of the cost model, then we can present the possible candidates to our users through the user interface. You have seen this pattern candidate browser. After ranking the pattern candidates, it provides a web-based user interface. Now, at the moment, we are working on better integration with Emacs. So I had the button on the interface to click, and the refactoring starts automatically, but that button does not work at the moment. So, this needs to be implemented. The good point in the pattern candidate browser is that it offers services for other software components in the system. It allows us to export data in different formats. It allows us to persist data that it produced. And it also allows multiple users to use the same code base and the same results of the pattern candidate discovery. As you have seen, we have to apply some shaping transformations as well before actually doing the map or farm introduction or pipe introduction. These shaping transformations might be quite tricky because we have to consider many syntactic forms and transform them into some canonical form before using the introscal refactorings. So, future work. Lots of future work. I think we have more future work than what we have done so far. So future work is getting always bigger and bigger. At the moment, we try to learn from bigger examples. I think this is the most important because we have already used small examples, contrived examples to test our tool with, but now we need big number crunching Erlang applications. If you have such an application, just please send it to us. As a conclusion,
You missed the most important thing.
yes?
We need a good logo.
A good logo, yeah. Kevin came up with this party name, but we need a good party logo as well, yeah. So the conclusion, we have shown you how to use Party, ParaPhrase refactoring tool for Erlang, beautiful name, without logo, that integrates the best of Wrangler and Refactoral. It can find us parallelizable code, not all of them, but some of them, some interesting ones. It can even predict the speed up if we turn these code fragments into parallel. It can offer refactorings that facilitate the introduction of these parallel skeletons, but it always expects the programmer to be partner in this activity. That's all, thank you.
So questions? I had one, and it was about the profiling. Could things be dependent on the size of data, for example, when you predict that you get a speed up of 20? I was thinking that it might depend on the size of the matrix, how many workers you might want to have, for example. Is that something you've taken into account?
Yes, but not very well. At the moment, we try to work with some fixed lengths, like 1,000 for everything. So there is a constant, but we need to develop a better measurement approach, which experiments with different constants, with different sizes, and tries to make statistics and decide which measurements are relevant or which are just, kind of bad values coming out from the measurement tools. So this is a weak point at the moment of our benchmarking. Yeah, we need to improve that. That's very important because the possible values that can flow into a function can affect very much the sequential execution time.
Yeah.
And if you measure like 20 and 120 and 5,020, you just cannot compute the average of these values because it makes no sense. So you need more. You need better statistical methods to get the right information out of these measurements.
Right.
We need to work on that.
Yeah. Interesting. Any other questions?
Doing these optimizations, it makes my program very specialized for the platform it's running on. Do you have any thoughts of how you could do it more general, so that you maybe get different constants for different systems, so that my program is still runnable on many computers?
So this is done by the calibration part of the course model. So if you want to calibrate your application for a given hardware platform, then you have to run this calibration module on that hardware and measure, for instance, how much time it takes to spawn a new Erlang process on that platform, how much time it takes to copy from heap to heap. So if you run your system on your desktop machine, then of course you should not use the calibration data that was collected on your machine. You have to run the calibration on the target machine and then use the data for the predictions obtained from those calibration. I hope this answers your question.
Okay, good. So let's say thank you again to Tamás.
Thank you.